Hello student. So let's try to solve one more problem from JEST 2022, and this problem is from small oscillation. So let me discuss this one. So there is two pendulum of length L and mass of both the bob for pendulum is M. They are simple pendulum. So this rod is massless and there is a spring attached at length L by 2. The length of pendulum is L. And the spring constant is given in term of weight of this particular bob. So that is mg by L. And for the small oscillation, we have to just calculate the angular frequency and we have to just find finally the ratio between the higher angular frequency to the lower one. So let's try to solve this one. So we can displace the whole system with some small angle, and let's say the first pendulum is making angle theta 1 and the second pendulum from the reference point means my vertical point is making angle theta 2 and this will be my spring. So this is my M, this is my M. So obviously we know the kinetic energy of pendulum. So kinetic energy of pendulum is basically half M L square theta 1 dot square plus, this is for first one, and plus half M L square theta 2 dot square. So this is kinetic energy. Now we have to write the potential energy. So the potential energy for pendulum is minus mgl cos theta 1 for first one minus mgl cos theta 2 for second one. And there is some restoring force in this spring also. And the restoring force in spring is all about half k into change in length square. So if we will see the change in length square, then this distance and this distance is the difference between this distance is change in length square. So this will be half k, and we have L by 2 sine theta 2 minus sine theta 1 whole square. So this is my potential energy. So in the kinetic energy, there is not any problem. They are written in a generalized velocity square term. So I can easily write the kinetic energy matrix, and this will be ml square 0 0 ml square. So these are 2 cross 2 matrix because we have two generalized coordinate. And then now the potential energy have functional form. So what do we have to do for the small oscillation? We have to use the Taylor expansion and we will just try to go up to harmonic term. So if I'm talking about harmonic term, that means we have to go up to square term of the generalized coordinate. So this is very simple. So we will go for minus mgl, and cos theta is 1 minus theta 1 square by 2, and our higher order term we are neglecting. Similarly, in the second one, mgl, and we have 1 minus theta 2 square by 2 and the higher order term, plus I am using this one. So here we will just go half k, and we have L square by 4 is there. And this sine theta 2, if we will go for the Taylor expansion, and here is a square there, then only we have to go up to first order term. So that value is equal to theta 2 minus theta 1 whole square. So now this is the thing, and here we will put the value of k. So if we will collect all this thing and put the value of k is equal to mg by L, then one L will cancel out. And finally, we have potential energy, and this potential energy is minus 2 mg by L, which is just a constant. So nothing we do with this. And if we will collect all the term, then you have mg L by 2, and we have 5 by 4 theta 1 square. You can just collect all this term. Similarly, we have 5 by 4 theta 2 square and minus theta 1 theta 2 by 2. Deliberately, I have chosen this one by 2 as common. Now we have to write the potential energy term, and we know that potential energy is symmetric matrix. So if we want to make it symmetric, what I can do, I can write this. This is constant, so there is not any role of this one. So if I will write it in a symmetric form, so mgl by 2, these are the diagonal one. So theta 1 square. This is again diagonal term. So theta 2 square. I can write this term as theta 1, theta 2 by 4 minus theta 2, theta 1 by 4. So we have this symmetric term, and now we can have potential energy matrix. So potential energy matrix is 5 by 4 mgl, and this is minus mgl by 4. This is minus mgl by 4, and this is 5 by 4 mgl. So this is my potential energy matrix. So after finding the kinetic energy matrix and finding the potential energy matrix, we have to solve the secular equation. And once we will solve secular equation, we can get the solution for, we can get the normal frequency. So let's try to solve the secular equation. So we have to remove all this part. So I need this t there. So I will keep t here. And these all things are not important. So what is secular equation? Secular equation is V minus omega squared t must be equal to 0, and we have to solve this determinant. So this is, so then we can find the normal frequency. So we have 5 by 4 mgl minus omega square ml square minus mgl minus mgl, sorry, minus mgl by 4 minus mgl by 4, and we have 5 by 4 mgl minus omega square l square, and this term will be 0. So now we have to solve this one. So this is very simple determinant we have to solve. So we can take mgl as common. So everywhere we can take it common, or we can solve it directly also. So there is not any problem. So 5 by 4 mgl minus omega square ml square whole square, this thing, minus mgl by 4 whole square is equal to 0. So from here we have a square minus b square thing. So we will use a minus b into a plus b. So we have 5 by 4 mgl minus omega square ml square plus mgl by 4, and we have again 5 by 4 mgl minus omega square ml square minus mgl by 4. So from here, if, and this must be equal to 0. So this must be equal to 0. So when we will solve this particular thing, then we can get the omega have two value. So first value is equal to, so omega have first value is omega is equal to omega 1 is g by L, and omega 2 is equal to root 3 by 2 GL, G by L. So you can easily solve it. First time you can add it, then that will be 1. So you have G by L, and you will subtract it. Then you have 5 minus 4, that, so we can have, from here we have 3 by 2 GL. Okay. So this will be your answer, and we have to find omega 2 by omega 1. So omega 2 by omega 1 is equal to 3 by 2 root under. So this will be our answer. This will be 6 by 4, and this will be just 4 by 4. So this will give you G by L. So this will give you root under G by L, and this will give you omega root under 3G by 2L. So from here, we can easily get. So the final determinant is also important, but most important thing is how you will write the potential energy matrix, how you will write the kinetic energy matrix after using the Taylor expansion of potential energy and kinetic energy. So this type problem is one of the favorite into JEST examination. So you have to practice this type problem. Thank you.